Hi, this is Rob Hetland. Today I'm going to show you 3 things that you can do using the Python programming language that are difficult to do in MATLAB. The motivation is to give you some ideas about the capabilities of Python and encourage you to consider it if you're a MATLAB user. So the first thing I'm going to look at is a thing called array broadcasting, and that is a way to multiply 2 arrays together that have a different number of dimensions. This is a problem that happens quite a bit. Suppose that I have a model grid that has different areas for each grid cell, and we'll say that we have a model grid that is 50 in the y direction and 100 in the x direction, so we'll have a number of random points that are my delta areas for each grid cell, and I have a 3-dimensional array, temp call it, that has the dimensions of 30 vertical layers, 50 horizontal in the y and 100 in the x, and I'd like to multiply these together. Now the way to do that in MATLAB is to do repmat on the DA matrix, basically multiply it by itself 30 times, and to get a new 3D array that you then multiply by temp. In MATLAB, what you can do is you can just say the result is equal to temp times DA, and it works. What it does is it will broadcast this DA array across each of the 30 levels in temp. Now, this is actually a simple example. You can broadcast arrays over any number of things that share dimension lengths but don't necessarily share the number of dimensions, as long as the non-matching dimensions are singleton dimensions. So that's very easy. There's no need to create additional arrays. The next thing I'd like to look at is a way to use multiple color maps. The Matplotlib programming package allows you to use a number of different color maps for different layers of a plot. So let me illustrate. We'll make a little grid. And then make two different functions on that grid. So we'll say the first one will be cosine of x times sine of 2y, and then another one will be 3 times cosine x times y times sine of y. Now we can do a p-color of the first one, x, y, z, and we'll give this a color map, jet, everybody's favorite color map, and we'll do the faster p-color mesh. There it is. Now suppose we want to put contours on top of this. Well, first of all, let's put a color bar on this just so we can see what we're looking at. Beautiful. Now suppose we want to put contours of our other matrix, ZZ. In MATLAB, you'd be required to have contours that are also in the jet color map. Here we can just say contour x, y, z, z. CMap is equal to CM gray. And there they are, the other contours. And we can also, color bar, spell it right. So we have now legends for our p-colored array and for our contoured array on the same plot. Of course, you have control over where these color bars go and over all of the different color maps that are in your figure, and you can add as many as you like. The third case I'd like to show you is how easy it is to do wrapping of C or Fortran. So I have a simple Fortran program here. It solves the Laplace equation. It will step the Laplace equation actually one time, given dx and dy, and it will give you an error, which is the sum of all of the differences that you had in your Laplace step, and it will return that. So basically, this is a standard Fortran function. The only additions you need to have are this C, F to pi comments, that tell you whether the intent of the variable is in or out or both in and out. So how do you compile this so that Python can use it? Well, here's my equation. I use the script called f to pi. I want to compile it. I want to create a module called Laplace, and I will compile my program Laplace.f. Now I want to use the G-Fortran compiler, so I'll say f compiler is equal to G-Fortran. And this runs the script that compiles it and creates a library, Laplace.so. Now I can import that just as I would any other Python program. Oops, just Laplace. And I can say Laplace. And I can see that time step is now in this package Laplace, and it will be the subroutine right here. You could have more subroutines in this file, and they would show up as part of this library that I loaded called Laplace. Now when I look at this, you can see that it gives me a function signature right here. I need to give it u, dx, and dy, and it returns u and the error. Notice that I don't need to give it n or m. F to pi figures that out automatically and inputs n and m based on the size of the array that I feed it. So let's try this out. So dx is equal to 0.1, dy is equal to 0.2, u is equal to random 100 by 200. Now I can just say u and next is equal to Laplace time step u dx dy. And there it is. That's all I needed to do. Now I could iterate this over a few times. I can say for n in range 100, iterate this 100 times, u next error is equal to Laplace u dx dy, print error, so we get some idea of the convergence. Oh, I forgot to say time step here. So you can see I've forgot to put u next in here so that we were using the array over again. There we go. So now you can see that the error converges over time to be something fairly small, and I can decolor mesh the first array and the final array. And you can see that indeed the Laplace solver, except for the boundaries, which doesn't include, smoothed out the middle, just like we'd expect. So that's all there is, and I hope you have enjoyed this example and consider Python if you're a MATLAB user. Thanks.